There was a time when a meteor flashing through the sky struck man with a deep sense of wonder. Even today, man's reaction to a meteoric display is likely to jam the switchboards with reports of imminent invasion from space. But as heirs to the knowledge, disciplines, and apparatus of the scientific revolution, we are familiar with, and at least partially understand, the meteoric phenomena. A meteoroid traveling in space outside our atmosphere remains unseen by man, for the molecules in space are so dispersed that collision with them causes no visible effect. If its trajectory traverses the Earth's atmosphere, it becomes a meteor. Here it begins to collide with more molecules. These collisions become more and more frequent as the meteor descends into the denser air of lower altitudes, causing it to decelerate. Each collision converts some of the energy of motion into heat energy, and the heat continues to increase until the meteor itself becomes incandescent, scribing its visible path through the night sky. Destroyed in the atmosphere by this heating, most meteors present no danger to man. Now and then, one is large enough to survive its passage through the atmosphere to Earth. It is then called a meteorite, and some are very large indeed. Dr. Peter Parameter became interested in meteors early in his career, and once wrote a paper titled,
"A thermokinetic description of bodies in passage through a plastic medium of nonlinear density at random velocities and angles, which could be just about summed up with this equation."
With this equation, his fellow scientists and designers are able to explain the effects of atmospheric penetration on differing bodies, those with different ballistic coefficients, at various velocities and angles. For example, if two bodies of different weights enter the Earth's atmosphere with the same velocity and entry angle, both the heavy body and the light one will begin to heat up at the same time. But impacts of air molecules slow the light body sooner. This deceleration of the light body occurs at higher altitudes, while the heavier, more energetic body penetrates deeper before it reaches peak deceleration. The total amount of heat generated by the lighter one is less than that generated by the heavy one, whose larger mass gives it greater kinetic energy. Two identical bodies with the same velocity entering the atmosphere at different angles also will decelerate at different rates. The steeper angle causes a more rapid encounter with the dense air, resulting in more abrupt deceleration. The total heat generated will be the same for both bodies, but peak heating will be less for the shallow entry. With identical meteors entering at the same angle but with different velocities, the faster meteor, under heavier bombardment by air molecules, will have greater deceleration, generating more heat and at a higher rate. But Dr. Parameter is no longer merely an observer interested in understanding the phenomena of meteors. A meteor is just an aimless traveler in space. Doc finds himself now involved in designs with a purpose and an aim. A missile has a target, and a spacecraft has a destination, a journey's end. To these, Doc applies his knowledge. He knows natural phenomena, both of aimless meteor and aimed missile. He knows that as they traverse the atmosphere, they heat up. If the heating or deceleration of a vehicle is excessive, the mission is threatened. Man cannot change the laws of nature, so he must use his knowledge to work within those laws. Doc Parameter knows that the two natural enemies to successful atmospheric penetration are deceleration and heat. He can fight these enemies on two possible fronts. First, on the design front by modifying the vehicle's shape and size relative to its weight. In other words, its ballistic coefficient. And second, on the program front by altering the vehicle's trajectory, its velocity, its attitude, and its angle of entry into the Earth's atmosphere. Dr. Parameter is now ready to use his technology to plan a successful re-entry for an ICBM warhead. He knows that of the two natural enemies, deceleration and heat, high deceleration is not a problem with a warhead, but too much heat could destroy it. He first surveys the project on the program front. He knows that the re-entry velocities and angles are essentially set by the mission. But to reduce heat load, the velocity of the re-entry vehicle could theoretically be reduced by firing a retro rocket. On investigation, he finds that in order to decrease re-entry velocities sufficiently by this method, a retro thrust system would be required weighing many times the weight of the warhead. This method is out. He next considers the possibility of changing the re-entry angle. He knows that a shallow angle will lessen the peak heat load by stretching the heating over a longer period of time. But the total heat generated will be the same either way, and the vehicle could absorb even more heat during this longer re-entry. Furthermore, a shallow re-entry angle has other serious drawbacks. First, a shallow angle impairs accuracy by deflection in the atmosphere. Second, it affords more time for enemy interception. A steep re-entry improves the missile's chances of avoiding interception and of reaching its target with minimum atmospheric deflection. In this case, altering the program is not the answer to the heat problem. Dr. Parameter must attack the problem of heat on the design front. Logic would seem to indicate that fast travel requires a streamlined shape to slice its way through the air. At subsonic velocities, this is true. But at supersonic speeds, the moving vehicle displaces air molecules which bounce off, forming a shock wave. As speed increases, the shock wave becomes more severe and heating increases. An ICBM will have a free-fall re-entry speed in excess of 23,000 feet per second. At this speed, the heat of molecular collision and friction, shearing of air molecules, is concentrated in a narrow zone along the surface of a streamlined vehicle. The heat generated may cause the temperature to exceed 15,000 degrees Fahrenheit. To combat this terrific heat, Dr. Parameter designs instead a re-entry vehicle with a blunt frontal area. The blunt shape creates its shock wave somewhat ahead of the vehicle. This occurs because the atmospheric molecules colliding with its frontal surface bounce back and intercept others coming in, setting up a kind of picket line in advance of the warhead. The peak heat is generated in this area away from the surface of the vehicle. Although the blunt shape decreases the peak heating of the warhead to half that of the streamlined shape, it will still heat up to 7,000 degrees Fahrenheit, much too hot for unprotected warhead structures. To further reduce heating, Dr. Parameter must find other techniques in addition to the blunt shape. His first solution is the heat sink. Use the blunt design and add a mass of heat-conducting metal large enough to absorb most of the heat generated during re-entry without melting before impact. It works, but he is not yet satisfied. The weight of the heat sink displaces more than 1/4 of the payload. Furthermore, the blunt design slows the missile, keeping it in the atmosphere a longer time, making it less accurate and easier to intercept. For the greatest accuracy and shortest time in the atmosphere, Doc knows that the streamlined shape is the best, but the heat sink cannot absorb and distribute the sudden extreme heat generated during the re-entry of a streamlined vehicle. Doc reasons,
If the heat cannot be absorbed, why not eject it as fast as it's generated?
The answer is ablation.
Ablation. Coat the frontal surface of the streamlined missile with layers of ablative material composed of fibers, resins, and ceramics.
This ablative coating protects the missile from the extreme heat in several ways. It is a poor heat conductor. Its surface gradually melts away, taking heat with it, and its vapor forms a thin insulating layer, deflecting some of the heat from the surface. The ablative principle combats the heat problem effectively and permits steeper re-entry angles while adding a minimum of weight. The streamlined missile, with its increased speed, affords the least possibility of interception and the greatest accuracy. It does produce a huge deceleration factor approaching 150 Gs. Fortunately, this poses no threat to a warhead. But for manned or other recovery missions, the G-load is a most important factor. For manned re-entry, this force should be held below 10 Gs. A shallow re-entry angle of about 1 to 5 degrees is the simple answer. The shallower the angle, the less the G-load. But this will be sustained over a longer period of time. This means a longer time at high speed through the friction of the atmosphere. Let's take a moment to see why this is not desirable. Dr. Parameter?
Thank you. Gentlemen, we have here a kettle of water. Heathcliff, we can use you in this experiment.
Oh boy, an experiment.
Thank you, sir. Now, if we may have another kettle of water and your stand-in. Thank you. Now we'll proceed with the experiment.
Experiment?
We'll add the same amount of fuel under each kettle, but alter the form of the fuel under one kettle to make it burn faster. We ignite both at the same time and compare the results. Splendid. Now, I'd like to point out that the fast-burning fuel, although reaching its intensity quickly, exhausted itself quickly. The heat absorbed was negligible. The slow-burning fuel, on the other hand, gradually increases in intensity. It will generate the same total heat load, but over a longer period of time, and you'll notice more heat is absorbed. Whoa! Thank you, Heathcliff.
Thank you, Dr. Parameter. So although the peak heat generated in the shallow re-entry is less, the capsule is in the heating regime for a longer time, and without the utmost protection would absorb an intolerable amount of heat. For manned re-entry, Dr. Parameter overcomes the deceleration enemy through program with the shallow angle, but he must combat heat on the design front. A blunt shape to cause a detached shock wave, a picket line against heat, and ablative materials for additional heat control. The doc is confident his new design will fulfill the requirements. Now to try it out. He wants low peak deceleration, so the shallow re-entry path is mandatory. This brings him down safely, if a little off target. To achieve some control and accuracy as well as safety, Dr. Parameter has been working on other design concepts, particularly shapes that produce lift. He knows that a ballistic missile is designed and programmed to hit a particular point on the Earth's surface. A manned ballistic vehicle with the same objective is much less accurate due to its design and long, shallow penetration. But a lifting vehicle, which is capable of descending at a still more shallow angle and with an extremely low deceleration rate, is able to change direction. This control gives it wide selectivity of landing sites within a large footprint area. For the shortest range within the footprint, the vehicle is pulled up into a maximum lift attitude at re-entry. This induces maximum drag, causing a steeper, more abrupt descent. For the longest possible range, the vehicle must assume the attitude of maximum lift over drag ratio. This footprint, huge at first, shrinks gradually as the vehicle descends. Dr. Parameter, while considering the advantages of lifting vehicles, is also aware of their drawbacks. First, the lifting structure itself imposes weight penalties, which compete with the all-important matter of payload. Then, Lifting vehicles may also spend up to 20 minutes in the heat regime, and being more streamlined, they require a still more complex heat protection system, competing still further with payload. Dr. Parameter, with his associates, has studied the strategy of atmospheric penetration. He knows its natural enemies, deceleration and heat, and has met them on the two fronts of program and design. He has accomplished important objectives. For the intercontinental ballistic missile, the objectives are rapid atmospheric penetration and accuracy. The warhead's natural enemy is sudden, intense heat. Its program, high velocity, steep re-entry. Its design, streamlined with ablation to combat sudden heat. For a manned or other recovery mission, the objectives are, first of all, safety, and then control. The mission's natural enemies, high deceleration, sustained heat. Its program, shallow re-entry for low deceleration. The vehicle's design, blunt, yet with control capabilities, a maneuverable lifting shape. The resulting long duration within the heat regime exacts a weight penalty because a complex heat protection system is needed. There will always be problems to solve. Dr. Parameter has worked out successful compromises so far, but he is still puzzling, still exploring. He plots his graphs, his curves, and flings them boldly into space. But he knows that we have barely gotten our little toe into space, and he constantly seeks to improve that toehold. He must hold to the possible, yet he constantly works along its impossible edges. He has opened the way for man's safe re-entry into the Earth's atmosphere. Journey's end for space travel.